So that's the idea of conditional probabilities. But why does this equation hold, right? Why can I find that conditional probability as the intersection of those two events divided by what I'm conditioning on? So I'll try to give a visual. We'll get a couple of these. We'll return to this idea even on Wednesday, but I think this one will give a pretty good idea of why we can write it this way. Okay, well, there we go. So I've been drawing up to this point circles to represent the events. They don't have to be circles. I could draw them, it could be any shape. So I'm going to use rectangles here because I think it just helps fall in line with the numbers a little bit better. So let's say this entire area here, let's say is event A. And I tried to draw this in such a way that it looks like it's exactly half of the entire experimental outcome space, right? So let's say like 50% of the outcomes are in event A, okay? Let's say I then take this like little rectangle or square over here, and I'm going to call this event B. Okay? So what is the probability of A intersected with B? Well, I tried to draw this to like exactly split it in half. So really this rectangle of B, which is entirely intersected with A, the way I do this is a very extreme example, right? I'm trying to draw proportionally. Let's say it's 0.25, right? Like you can think about like you have two squares here and then like a large half up there. So if I ask you for just what the conditional probability of B is, right? Well, this is a unique scenario in which all of event B is within A, right? So if I'm thinking about event B, it's really the same as the event B intersected with A, because I'm drawing this as an extreme example. So we call this the unconditional probability of B. Oh, sorry. Try to get this all in one line here. Okay. What if I want the conditional, so we'll call this is the conditional probability of B. Because we're still looking for the probability of B, but we've now conditioned on something else. Okay? Well, if the area of B intersected with A is 0.25, and now that I know A has occurred, essentially what I'm saying is the entire experimental outcome space is no longer 1 because I'm telling you that A has occurred. So now the only outcome space left is 0.5, right? Or whatever the probability of A was. So here, we can think about the entire experimental outcome space left is no longer like out of 1, it's only out of whatever the probability of A is. Right? And what's the probability that now that we know we're somewhere in A, what's the probability that we are in B? Well, out of this entire space of 0.5, 0.25 of it would be that I end up in event B, which is really wherever probability in A and B intersect. Okay? Now I drew this one as an extreme example so that all of B was within event A. Okay? So here it was kind of odd because the probability of B and the probability of the intersections were the same thing. Right? But what if that wasn't the case? Would this idea still hold? Well, let's go back here. Let's say now the probability of B, let's say I make it 0.3. But I just extend it up here, right? So now the intersection of A and B is still 0.25. And now when I condition on A, it goes back to the exact same thing, right? Because saying that I'm conditioning on A eliminates all of the possible outcomes that weren't in A, right? So that's why we don't use the probability of B here in the numerator, where we just use the probability of the intersection of A and B, right? Any questions on that? Well, it's kind of a lot. Just trying to give you an intuition behind why that equation holds, okay? Because it's essentially like once we condition on this other event, we're like limiting the space that we're looking at, okay? And I could actually come up with like a really crazy one. Like, let's say event B was actually all the way out here, right? Well, then it doesn't matter, right? Because once I condition on A, I'm still back to the same thing, right? It just matters where the intersection of those two events are.